This is my first paper analysis for Compix 529-21B, Engineering Self-Adaptive Systems. My name is Blake Wyatt. The name of this paper is Generating Environmental Models for Testing Self-Adaptive Systems. This paper's authors is Zhengchuan, Liang, and Zhengchuan. The paper was presented at the Proceedings of the 11th Asia Pacific Symposium of Internetware in the year 2019. So, what is the problem this paper tries to solve? The primary issue the authors of this paper are attempting to resolve is the discordance between environmental and software solutions when it comes to self-adaptive systems. As we enter the current year, many devices are being built that are solely reliant upon AI and self-adaptation to be able to navigate, enhance, and survive in their environment, ranging from devices such as Google's automated car to the autopilot of a Boeing 747. And although we are creating solutions to these, we are encountering troubles as society as we haven't developed a proper testing environment for such devices. The objective for the authors is to create a testing environment where you can test self-adaptive systems no matter the outward context of the environment. This testing method has been coined AutoModel. The goal of AutoModel is to build an updated environment from the perspective of how the environment acts with the system instead of the entirety of an external environment. Why is this still a problem? Self-adaptive systems have many more variables to deal with than an average piece of software. One of the primary goals of self-adaptive systems is to be able to adapt to the environment that's been allocated, which is a big issue for many pieces of software. No longer primarily worried about bugs that have been created from a software developer, now we have to test that the self-adaptation of a device is accurate and concise to the environment that's been designed for. Empirical evidence has shown that self-adaptive systems can be heavily error-prone, creating many false positives, which is further elaborated upon in verifying self-adaptive applications suffering uncertainty by W. Yang, C. Zhu, Y. Liao, C. Chao, X. Ma, and Zhe Lu. As of right now, we've currently had two major ways to test for errors. The first being the real physical environment that our product is intended for, and the second being the simulated environment. Currently, real environments aren't cost-effective, have difficulties when it comes to replicating issues and identifying where the adaptation went wrong, and impossible to cover an exhaustive list of potential issues and errors that can be faced outside in a real environment. The second is a virtual environment. Currently, to improve the productivity, many self-adaptive system platform manufacturers provide their own simulators. Some others provide modules that can be used in third-party simulators. Considering that as an environmental simulator provides much better observability and controllability than the real environment, currently, though, there's still a gap that needs to be bridged between the system's environmental simulator and that of its real running environment. The primary issues with this currently is that developing a digital replica real-world environment is nigh impossible. So what have others done before this paper? Real-world testing. Before this, the primary way to ensure that a product is viable for market is real-world testing. Though compared to AutoModel, there are many significant disadvantages. This includes cost, time, effort, and danger. When something like this comes as a real-world expense, every potential issue can lead to a huge cost. Whether this be a crashed car or downtime on a server due to incorrect adaptations. Time is a significant element due to not being able to set a perfect test environment for an aspect you wish to test, and if for a physical item, space to do so. And danger being another key factor. A potential issue of testing many of these physical items' interactions in the real world is a potential danger that an issue can confer on reality, whether it be the resources that go wasted and contribute to pollution when it comes to manufacturing costs, or the potential loss of human life when an issue goes catastrophically wrong. For instance, with Google's self-driving car only in the year 2016, they conducted over 600,000 miles in-field testing for its Waymo's self-driving car, and 124 disengagements happened during this test driving period. The second option is the real-life simulator. Currently, the only alternative is to test a self-adaptive system on an environmental simulator. Well, the goal of the simulation is to balance time by creating an emulator as close as possible to that of a real environment. Many self-adaptive manufacturers provide their own simulators and modules. Although much research has been dedicated to this topic, there's still a significant gap between the simulator and the real environment. This shortcoming means that it's fine to achieve assessments of situations that are difficult to create in the real environment or an initial test to identify hypothesized shortcomings, but not for an actual conclusion about an issue that they're facing. The main idea. AutoModel. The primary concept of AutoModel is instead of developing the external world to one in a digital space, we instead create a digital environment that only considers the aspects of the external environment that would have an impact on our device. By regarding the system's execution traces as the environment's execution traces, AutoModel uses model synthesis techniques and data-driven approaches to build a simulated environmental model. How this will be achieved is through 3 steps. Phase 1, trace collecting and pre-processing. Phase 2, logic learning. Phase 3, model building. Trace collecting and pre-processing. Collect execution traces of the target self-adapted system and regroups recorded iterations according to their sensed environmental inputs. Each group records the environmental behavior under different situations. Logic learning uses linear regression to learn the environmental model's logic under different situations. We build the environmental model. The identified environmental situations become the states of the derived environmental model. For each state, the environmental model uses the learned logic to interact with the target self-adapted system. How is this better or different than existing solutions in the state-of-the-art? The primary difference in AutoModel and current environment testing devices is that it uses execution traces self-adapted system to represent the behavior of the system's running environment, rather than attempt the whole place to replicate the environment. This leads to it being a much cheaper alternative to that of the current simulators that are currently available through software developers. The current way that's being implemented isn't truly representative of the real-world environment either. Instead, it's used as a bridging point to develop software to the extent where it can be tested in a real-world environment to see if there's any issues. What AutoModel aims to do is to get rid of the bridging step and have a digital environment that can fetch results that are representative of the real-world environment. How do they evaluate this? The authors tested the AutoModel by running tests replicating using gyro sensors to create a linear regression model that can run through the 3 phases. After collecting this data, they implemented a statistic technique called the coefficient determination, known as R-squared. This is proportion of the variation of the dependent variable that is predictable from the independent variable. The long, short, and tall of the coefficient determination is the close to 100%, or usually what it is. The more representative this is future outcomes based upon total variations of outcomes explained by the model. Through the testing that the authors did, the final outcome was 80%, 86.8%, and negative 1.8%. Negative 1.8% implies that it failed to replace the real-world environment in this one aspect. But the authors suspect that it's up to the time measurement of 1 second they implemented. But in saying this, the overall outcome of the test still holds a strong R-squared value of 55%, which is infinitely better than prediction accuracy of a random model, whose predictive R-squared tends towards negative infinity. Critique. The big negative in the room. Not rerunning the test that fetched a significant negative value to me seems like a real unethical situation. Repeating the test environment but changing the value to be less than 1 second for the timing interval seems like something in the realm of possibilities which wasn't done, which is very odd and strange to me.